Right now, countless background scripts and machine clients are quietly fetching resources across the internet, pulling down data to keep modern automated pipelines running. Suppose an automated script is tasked with pulling a study guide. It reaches out across the cloud for a specific target, a document named AZ900_studynotes.docs. Instead of the Azure study notes, the terminal returns the raw HTML of a Google SSO login prompt. The phrase "sign in to continue" is a stark anomaly. Scripts expect raw data payloads, like compressed XML, not an HTML identity challenge. We can treat this unexpected response as a pristine forensic artifact generated by modern access controls. The script hit a hard programmatic stop, dictated by zero-trust architecture. In older network models, being on the right corporate network or VPN granted access to files. Zero-trust discards the physical network wall entirely, requiring continuous identity verification regardless of where a request originates. Analyzing the exact text of this rejection allows us to reverse engineer the specific security mechanisms that blocked the fetch request. To see exactly what the API gateway saw, we have to look at the precise moment the script's request arrived at the server. The incoming automated request contained the correct URL, but it arrived without a valid cryptographic bearer token. Reacting to the missing token, the gateway triggers a hard block. Instead of dropping the connection, a 302 redirect forces the traffic away from the payload, routing the client directly to an identity provider to demand cryptographic proof. This forced detour reveals a key design choice in cloud infrastructure. The target document itself sits behind no traditional network boundary. There is no firewall shielding the specific file path. The cryptographic access policy enforced at the gateway is the sole mechanism defending the resource. A simple HTTP GET request is effectively useless here. Without completing a complex authentication handshake beforehand, the request is dead on arrival. The sign-in text sitting in the terminal proves that the API gateway successfully defended the resource by defaulting to absolute denial. Further down in the scraped text, the identity provider asks for an email or phone. This decision tree maps home realm discovery. Once an email is submitted, the gateway reads the domain suffix to route the request. Internal domains route natively to Google Cloud Identity. External domains trigger Identity Federation, routing back to an external tenant like Azure Entra ID. This explains how an Azure user studying for the AZ900 exam can seamlessly authenticate through a Google-hosted gateway. Behind the scenes, the two competing cloud providers have established a cryptographic trust relationship that allows this handover. Protocols like SAML or OpenID Connect facilitate this cross-cloud handshake, ensuring that raw passwords are never passed between the different environments. The user experiences a simple, static text box. The backend executes an invisible global routing protocol. That mundane email prompt operates as a massive multi-cloud router, dictating the flow of identity federation. The scraped login page concludes with a secondary warning. Not your computer? Use a private browsing window to sign in. This text shifts the defensive focus away from backend cloud architecture and directly onto the vulnerabilities of the physical endpoint. The instruction relies on session ephemerally, which acts as the primary defense against localized threats on shared or compromised physical devices. This compares persistent browser states versus private sessions. Standard cache saves authorization tokens to the local disk, where physical access allows reuse, bypassing cryptographic checks. Private windows force memory isolation in a sandbox. Closing the window forces unrecoverable destruction of those localized tokens. Multi-billion-dollar cloud identity and access management systems explicitly rely on these localized browser-level memory constraints for complete security. The most secure cloud perimeter collapses if the localized endpoint state is persistently compromised. This wide architectural map shows the sequence: the unauthenticated request on the left, OAuth routing in the center, and the locked payload on the right. A failed fetch reveals the IAM gateway layers, from redirect to identity handshake. In a multi-cloud environment, physical resource hosting and identity verification operate independent of one another. Knowing the exact URL or residing on a specific network location grants zero access to the data. Every step of the journey requires continuous cryptographic verification to proceed. Maintaining the integrity of that global cloud boundary relies heavily on localized endpoint constraints. The system is built to actively reject unauthorized intrusion. A basic login screen is a thin veneer covering extreme cryptographic complexity operating directly beneath it. For systems engineers, analyzing precisely how a system rejects a request provides the clearest possible map of the security perimeter. In a zero-trust architecture, this specific rejection confirms the system is working. Sign in to continue to Google Drive. Email or phone. Forgot email? Not your computer? Use a private browsing window to sign in. Millions stare at this exact screen every day. They type their credentials on autopilot without reading a single word on the page. It is easy to assume this is a basic digital form, a few text boxes piping keystrokes directly into a backend database. These 4 lines of text serve as the entry point for a sophisticated cryptographic architecture designed to manage digital identity across the globe. The internet was built on a persistent architectural flaw. The HTTP protocol is entirely stateless. Because of this stateless design, servers suffer from continuous digital amnesia. They instantly forget who a user is after every single click. To fix this continuous amnesia, engineers have to build a state machine, a persistent bridge that remembers user context across separate, isolated requests. The entities that construct and maintain these massive state machines are called identity providers, or IDPs. An identity provider must weave and force a continuous thread of trust over a network protocol that is structurally disconnected by design. That mundane block of Google login text from the introduction is the literal command line interface for one of these massive identity provider engines. We are going to execute a line-by-line deconstruction of this text to expose the hidden architecture running beneath it. Tearing down this interface is the best way to accurately map the mechanics of cloud authentication. Look at the opening phrase, "Sign in to continue to Google Drive." The word continue is a deliberate user interface illusion designed to mask the backend mechanics. At this exact millisecond, you are no longer communicating with Google Drive. This specific phrase signals a total halt in local application processing, forcing the system to defer your request entirely to an external authority. This interaction is governed by the OpenID Connect Flow, or OIDC, which defines the strict structural relationship between a service provider and an identity provider. This diagram shows a user node attempting to access the service provider, in this case, Drive. Because the user lacks a valid session token, the verification check is rejected. The service provider server reacts instantly by generating an HTTP 302 redirect command. That command forces the browser to instantly reroute the user away from the app and over to the identity provider's dedicated centralized domain. Attached to that rerouting URL is a hidden data packet containing highly specific destination parameters. This payload dictates exactly where the identity provider needs to send the user back to, but only after a successful authentication event occurs. Large-scale cloud applications require this external delegation of trust. It ensures that individual apps don't have to manage or store sensitive credential databases themselves. The act of continuing requires the local application to hand off all cryptographic authority to an external identity provider. Now shift the focus to the input directive itself, email or phone. There is a glaring omission in this design. There is no password field presented anywhere on this initial screen. Legacy login screens operated differently. They always requested both a username and a password simultaneously in a single unified form. In modern cloud architecture, asking a user to provide a password too early in the flow is now categorized as a critical security vulnerability. This input field serves as a routing mechanism, determining the specific network path the authentication request must follow. The missing password is a byproduct of the identifier-first flow. This mechanism relies on a process called home realm discovery. An automated sequence fires the exact millisecond the user submits their email address. This diagram shows a background string parsing engine immediately splitting the username prefix from the domain suffix. That extracted domain is fed into a high-speed database lookup, cross-referencing it against known network registers. The logic branches based on ownership, determining if the domain belongs to a federated enterprise workspace or a standard consumer account. If the database identifies an enterprise domain, it triggers a secondary hidden redirect, instantly routing the user to their specific employer's custom security gateway. The actual password is only requested after the correct home realm is definitively identified and verified. The simple email prompt is an automated network routing protocol disguised as a basic text box. At the bottom of the screen sits an explicit conditional warning. Not your computer? Use a private browsing window to sign in. There is a pervasive belief among average users, and even junior developers, that private browsing is primarily an anti-tracking tool designed for user privacy. Look at this browser feature strictly from the perspective of an identity provider attempting to enforce network security. In the context of authentication, private browsing is a mandatory hardware-level quarantine for untrusted operating environments. Upon successful authentication, the system generates physical data. It issues a JSON web token. This diagram illustrates an identity provider server generating that token, showing how a persistent browser session manages it to keep the user logged in between clicks. It executes a physical write process, storing the persistent token as a file directly on the computer's local hard drive. On a public or shared computer, this creates a critical vulnerability. Subsequent users can extract that physical file to completely hijack the active session. Initiating guest mode or a private browsing window alters this mechanical architecture. The browser strictly sandboxes the token into ephemeral RAM, completely bypassing the local hard drive. The moment that private window is closed, an instantaneous purge occurs. The system cuts power to the RAM, wiping the memory state entirely. This warning acts as a protocol requirement to ensure that session tokens remain isolated within volatile memory. This network map diagrams the massive structural infrastructure we just traced, a dense web of redirects, database lookups, and memory sandboxes. It requires incredible design elegance to hide this massive infrastructure behind a few lines of plain text. This extreme level of user interface abstraction is a strict requirement for global product adoption, exposing the true, jarring complexity of the OIDC flow and network routing protocols would completely paralyze the average user. The genius of modern security design is found in the total invisibility of its cryptographic processes. This hidden complexity anchors foundational cloud engineering principles, specifically those outlined in core frameworks like the Microsoft AZ900. Modern enterprise cloud environments rely entirely on the concept of zero-trust architecture. Zero trust mandates a paranoid default state. The system assumes the network, the hardware, and the user are all perpetually compromised. This simple login interface acts as the singular, heavily fortified checkpoint defending the otherwise vulnerable stateless web. Submitting this screen initiates a high-stakes cryptographic process that